Okay, so I think we can get started at this point. It's time. So first of all, a very warm welcome to this session. I know it's the last session, and I hope I can keep everybody awake here. And so yeah, today in this session, we are going to talk about Opti. I hope many of you may know what Opti is, but if you don't, I have got some few introductory slides for Opti, and I've got you covered over there. And here we are going to talk about how we are bringing Rust in there. So if you know about Opti, it has the similar like user space, kernel kind of stuff. And if you have seen a Rust development on the Linux side, it has come from the application side, and now it's penetrating into the Linux kernel. The similar kind of approach we are trying to do in the Opti side. So we are first starting up with the trusted applications and see the Rust benefits. First of all, the memory safety benefits that it offers, and really on the Opti side, because it is handling your critical security, critical data like keys, credentials, and things like that. All your critical operations happen over there. So yeah, memory safety benefits can really be a value add there, and it can really harden up the Opti environment. So yeah, we are going to talk about how we are bringing Rust over there. First of all, who I am. I'm part of Foundries team within Qualcomm. So Foundries is an independent subsidiary within Qualcomm, and it was recently acquired. So for me, my keen interest has been platform security. That has been like from my beginning of the career, whether it has been like the early boot code or the bootloaders or the firmware or the operating system. So wherever like system level security comes in, I usually get interested over there, and I'm maintaining few bits and pieces in kernel and Opti and TFA. And my other areas of interest, yeah, bootloaders, device tree, and some debugging like ftrace in Opti, and open embedded and Yocto. So first of all, what is Opti? So it is open, portable, trusted execution environment. That is like, it is running alongside your rich execution environment and offering like isolation properties. That is one of the main design goals for Opti. Like you have your application code running in the Linux, but you want to like isolate some critical pieces that is managing your keys or credentials or things like that, and you want to protect them against like attack vectors that are there in the rich execution environment or the Linux environment. You just want to isolate them in a hardware enforced environment. So Trust Zone has been there on ARM, that is providing that kind of isolation capabilities, and Opti builds on top of that. So yeah, there is like RISC-V support has been coming up in Opti, but yeah, it's still early stages. So anything like if there is an hardware enforced boundary that is present on a SOC, whether it's ARM or RISC-V, so Opti is going to be it's possible to enable Opti, and you can work on top of that. So the major goal is here is to provide isolation for your security critical code. And apart from that, the other goal is smaller footprint. We want to make like the trusted computing base, that is on the code that is executing in the Opti environment, to be minimal so that it's auditable, verifiable. It's it's of no benefit if you are going to add like rich network drivers within Opti environment and going to say it's a trusted execution environment. It's always like you keep it minimal and you keep only the code that that is expected to be there, and not like putting all of the code in there and say, yeah, it's a trusted execution environment. That's not going to solve the real use case, because you need to say that, yeah, this is the piece I trust, and this is what I can verify as well and audit as well. And the other design goal is about portability. Keep, we want to make it as much portable as possible, like very different platforms, we want to enable it as fast. And on the user space side, we have this trusted applications running in the Opti environment. We want them to be portable as well. So that's why we are following up this global platform T specifications that are, it is a standardized body in the T world that is creating specifications that usually all the trusted OS vendors follows. And yeah, if you follow them, then a trusted application written for one trusted OS can be portable to the other trusted OS as well. So that's what we try to follow. And you don't need an actual hardware to run Opti. You can use Camu. Camu provides that emulation for trust zone environment on ARM, and you can run Opti on top of that. So I have put a link over here, and you can go over that and get hands-on on Opti. So overall architecture for Opti, so as you can see here, on the left-hand side, we have the normal like rich execution environment or the Linux environment, and where the client applications are running. So with Opti, what we have done is like we have isolated a piece of code that is managing your security critical operations within the T environment, and that's what we call as trusted applications. And the underneath environment is just like providing the interface, how the client applications interact with trusted applications. You can think of trusted applications just like function invocations that are managed in a different environment, but they can be accessed by the client application as a remote function invocations, you can say. And on the stack that is there in the kernel, so kernel is providing this T subsystem that is providing the ioctls towards user space, and there is this T client API that is a library that is compliant with the global platform specification. And on the trusted execution environment side, we have this Opti driver. So you can plug in, like if there is another trusted OS, then you can have that corresponding driver in here underneath the T subsystem and enable that. But for Opti, we have this Opti driver here, and that is using this Opti message APIs. And currently it's using secure monitor calls for the ARM platforms. But yeah, for RISC-V as it gets added, so there would be kind of corresponding message passing calling conventions over there. And on the trusted execution environment, this is the core kernel that Opti has, and that's running again in a kernel kind of environment, but it is higher privilege than the Linux environment here. So this kernel is higher privilege level, and it has more access to the system and to the secure peripherals or the secure memory resources. And here we have this pseudo trusted applications. You can think of them like analogous to the kernel modules, but they are built into the Opti core rather than loadable modules. And on the user space side in the trusted execution environment, we have this APIs that are again T internal APIs as per global platform, and trusted application can use them to get various services from the Opti core. So these are again, you can think of them like ioctls into the Opti core and accessing various services over there. Now coming on to the communication stack, how this client application would invoke services, like get different secure services from the trusted application. So there are like 3 things here you need to keep in mind. First is the context. Context is like the client application opens up a context with the trusted execution environment as a whole. And afterwards, it's this session that is like one-on-one session with the trusted application. So client application can communicate with different trusted applications depending on whichever service is implemented by corresponding trusted application. And then there is this command. So this command is like function invocations into the trusted application to get corresponding secure services. And lastly is this shared memory. So we have the shared memory that can be dynamically shared with the trusted application, or it can be statically reserved as well. So that's how you provide zero copy kind of behavior. Now coming on to why do we need to Rust Opti? First of all, as I mentioned, memory safety can be a huge plus for Opti environment, and Opti is doing all the security critical operations that are, we are managing all the user and system credential keys and confidential data. And although we have all the boundary checks that are being done in the C code that's already there, but yeah, with Rust, that can make it more simplified, because many things Rust compiler can take care of it and warn users about it during the build time as well. So yeah, having Rust in now, first of all, the inception, how it came into picture for Opti. So thanks to the efforts from the T-Clave Trust Zone SDK project team. So they initiated this Rust support for the trusted application in Opti. And what they did was they added, at that time, so it was like 2019 or something like that. So at that time, the Rust standard libraries were much more popular, and it was the de facto that most of the Rust crates supported, and there wasn't like no stud wasn't much popular. So they added this custom Opti targets for trusted applications development. So what they did was like, because the trusted application environment is very minimal, it doesn't provide all the networking, thread support, and everything else. So they stubbed out everything based on this toolchain target for Rust. And but it made those trusted application bulkier. But what we have already in the C part, we have very minimal libc for trusted application, and they are very minimal. And but on the Rust side, with this targets, it was bulkier because all the standard library things are getting imported, but although they were just stubbed out, and they were less performant due to all those things compared to the C counterpart. And what it needed was there was a binding to a particular Rust toolchain version, because you have to keep porting that target to a different Rust toolchain target whenever you need to bump Rust version. So what it looks like with this SDK, so it's basically they have put up this wrappers on top of a T client API on the client application side, and on the trusted application side, these are wrappers. So these are just bindings to the T internal API, and sitting on top of that and providing an API, Rust API for the trusted applications to develop. And similarly on the client side, these are just standard client application with just allows this Teak APIs to be called from Rust code. And that's what it is. So I've put some snippets how it works. So this Opti Teak crate that can be used to open a context, open a session with the trusted application, and then you can set up an operation and do invoke commands. And these are just API wrappers built on top of the C library that is provided by Opti. Now let's look at why we need no stud here, because all of the difficulty that I mentioned with the custom Opti target for trusted application, no stud seemed to be a perfect fit, not only because it can allow us to support the tier 1 target toolchain for ARM64, and it also allows to address that small footprint design goal that Opti has. We just use the bare metal or Rust for trusted application, and only add the libraries that are actually needed, not like pulling in all the standard library in there and then stubbing out things. So it's rather better that we start from the minimal and add stuff as needed and keep the footprint minimal. And the other limitation, so Opti environment is pretty constrained. We only have few megabytes of RAM because we allocate all the RAM mostly to the Linux world, and for Opti world we just carve out some memory from there. It's particularly 64 megabytes or so on most of the platforms, and that makes it the memory available to trusted application even limited. So yeah, we can't like for like tens of trusted application, you put all the standard library over there, then you can't accommodate everything in the RAM available to the secure world. And we don't have like user space threading support and limited networking. We have like global platform sockets API, but yeah, those are all going back to a Linux to and hooking up on top of Linux sockets to provide the services. So we don't have networking drivers within Opti, but rather we use services from the Linux world to provide networking support for trusted applications. And similarly for the file system support, we don't have that, but yeah, we do have like the secure storage support that is based on RPMB or like remote file system services from the Linux side. So those are all the reasons why we thought no-stud is really what we need for trusted application, and that can make the trusted application a first-class citizens, and you don't have to worry about all that custom Opti target for trusted applications. Now, so after that, I got motivated, and I proposed this no-stud support in that SDK, so where all the Opti crates are being managed. And with that, we were able to see the performance parity with the C counterparts trusted applications, and the binary size reduction was also huge, about 70 to 80K. And even now with the kernel support getting in, the no-stud support is gaining traction. Many crates are adding support for no-stud. Even like the common crypto libraries are supporting now no-stud. So yeah, that makes it easier for trusted application developers to use that no-stud feature that is available in many crates now. However, the SDK still, as has been developed initially, it has support for those complex trusted applications that are using the standard libraries, but you don't need that, all of that. So that's what I'm going to demonstrate in further slides. So what you need for no-stud TAs is just these three crates: OptiTeak, OptiUT, and OptiUT build. So OptiUT build is a crate that makes it easier. So it is containing all the boilerplate code for the trusted application build. So the build script for a trusted application can just remain minimal. So this crate is for that purpose. And now I'm going to show you how you can just write your Hello World or trusted application using these crates, and you don't need to rely on any SDK or any custom toolchain target, just using the Rust Tier 1 toolchain target for ARM64. So first of all, as I said, these wrapper APIs, the Rust wrapper APIs, are built on top of the libraries that are provided by OptiOS for the trusted applications, as well as Opti client for the client applications. So what we need first is to have them compiled and set up these TA dev kit directory and Opti client export for the client application. Here I have compiled it for Camo. You can compile it for your platform of choice and write trusted application corresponding to that. So these are the variables that are being consumed by those crates, which I referred to earlier. So let's look at how a directory structure for Rust-based no-stud trusted application would look like. Here you would see this host refers to the client application. It's just a normal and simple client application, and it's just a Linux application. You can think of it like that. This proto crate, this is a protocol crate. So if you have already worked with trusted application, there is usually a header that is shared among the client application and the trusted application for all the invoke commands. This is the same thing. This is a library crate that is just having all those invoke commands IDs listed over there that is shared among this trusted application and the host application. So we'll look at that in a moment. And on the trusted application side, we only have the special build.rs that is using that opti build ut create to set up the environment for trusted application, because we have to like configure the stack space or the heap space for trusted application, because that's fixed. And yeah, apart from that, it's just like the normal application code. Now let's look at the different files in there. The cargo.toml for host client application. Here you could see it's just using this opti-teak crate, and this is the particular version, and this is the shared crate, the library crate, and that's it actually for the hello world or the client application to be written. And this is, you can see this concise trusted client application code, and this is what Rust offers us as well. The code can be very concise in nature. It's just showing, if you compare it with what we had with the C counterparts, it would be like half of that size, and it's offering much more ergonomic features that Rust offers. Here you could see here we are creating a context using this API that is offered by this opti crate, and then we are opening a session, and then in this hello world function we are just creating an operation and doing invoke commands. Here we don't have to deal with all close session and close context thing, because what it is going at the end, it is just going to drop, and in a drop for context, it is calling the T close context as well. So that's all happening, all taken care of Rust by itself. You don't have to worry about that. So yeah, that makes it very, it makes the development very much simplified, and yeah, that's what I loved about it most, the majority of thing about Rust, and apart from the memory safety benefits that it offers. And this is the make file, and yeah, here we are just doing cargo build. You would notice here we are setting up the linker because of cross compilation and for this client application, and yeah, that's all we do. But yeah, it's just like normal cargo build command for the client application. And this protocol crate, here again, this is the cargo toml, and we are just using this crate num to define those invoke commands. And this is the library crate. So here you see we are just defining those invoke commands. This is increment value or decrement value. These are the two commands we support here as of now. And here we are also mentioning this UUID. That's what is used to identify the trusted application, and it is being shared among client application and the trusted application. Now coming on to the trusted application code itself. Here you would see it is depending on opti ut crate, and that's the particular ut version. And this sys crate is also in this opti ut crate that's provided by the same. And yeah, it's the system crate there. And there is this build dependencies that is using this opti ut build. This is containing all the boilerplate code for the trusted application environment. And yeah, these are all the features that you can set. So we have set up the link time optimization here. And yeah, that's all you need. And on the trusted application code itself, so if you have worked with the C counterpart, we usually have like four to five functions that have to be implemented by a trusted application. It's not like a simple like a Linux code where you have a main function and it starts from there, but it is like having multiple entry points from the opti code. So there is like create entry point, destroy entry point, open session entry point, and things like that. So we have the similar entry points in Rust, And here we are using the procedural macros that are offered by Rust. So these are all provided by the opti-ut crate. You just need to define these APIs, and every trusted application have to define these functions. And here we say that when the trusted application gets created, what's going to happen, and you can do things in here. And when the session is opened with the trusted application, what's going to happen then? There can be some parameters that can be passed during open session, and trusted application can work on top of that. Similarly, on close session, now the main crux part is this invoke command. That is the main function that is actually executing all the functions that trusted application is providing services for. So here you would see we are implementing those invoke commands, this increment value and decrement value, and uh, this is just an implementation of invoke command, and here you see we are just incrementing the parameters that are being passed by the client application and decrementing it. But yeah, this is just a simplified example, and you can do many more things in here if you have already worked on the C counterpart. So it's just demonstrating that, yeah, how the Rust code would look like for a trusted application. And then you have like destroy entry point for a trusted application. It's like when you kill a trusted application, then you can do some housekeeping over here. Yeah, and this user TA header, again, this is provided by the opti-ut crate, and this is just defining the boilerplate, like the entry point for the trusted application and things like that. So yeah, we just need to include it within the trusted application code here. So that's all about the trusted application code. Now, this is a simplified build script for the trusted application. This is using this opti-ut build crate to build the trusted application. And here we are using this default configuration that is like in there in this opti-ut build crate. But yeah, you can always go ahead and modify the default config options. Say, for example, you need to increase the stack space, you need to increase the heap space. You can always use the APIs provided by this crate to override the default configuration, or you need to set up the flags like it's a multi-session TA or something like that. So those all can be overridden, and that all of them are provided by this opti-ut build crate. There is a reference for you if you want to see how it works and how you can kind of modify different config parameters for a trusted application. And lastly, this is the make file. Here again, you will see it is cross-compiled. That's why we are setting up the linker for the Rust compilation. And the last thing here, you will see we are signing the trusted application as well. That's usually all the trusted applications which are loaded by Opti that are signed and verified during load. So we have to sign it, and we are using the TA dev directory that is provided to us. So here you see we are using the script from there, the TA dev directory. You remember we compiled OptiOS, and from there we are using the script to sign the trusted application that is generated, and you will find the same like uuid.ta file afterwards. So now one thing to note here is when I added this no stud support, there were some like variable that were the C type variable that were supported by the nightly toolchain, and we still haven't migrated to the stable toolchain. So yeah, that's a step we need to do. But yeah, apart from using nightly, you can just add a target for the tier 1 target for ARM64, and you can just compile your client application as well as the trusted application. And client application would be, after you run this make command, it would be present in this folder. And similarly for trusted application, now what you need to do is just transfer these client application and trusted application to your root file system, and yeah, just invoke there. So yeah, you can do test them out on Camel using the instruction which I had listed before. But yeah, this is all you need to do. And you don't need to, like, as I said earlier, you don't need to worry about using that SDK and everything else, but use the standard crates and use the tier 1 toolchain for Rust development. Now, first of all, we have the future work, and there is a lot to do on the Rust side with Opti. And we have just started, I would say. But yeah, first of all, there should be stable toolchain support for trusted applications. And then the next step for me, for the trusted application to be written in Rust, to be portable actually, we need like some standardized specifications, like Rust APIs that are standardized from global platforms. Similarly, like we have on the C counterparts, we need a standardized Rust APIs so that we don't have to rely on those wrappers as of now, rather than we write kind of a Rust library for Opti from scratch and using whatever ioctls are provided. But yeah, that is going to take a long time. I think people would realize, and the standardized bodies would realize, yes, we need to have a common API so that the Rust trusted applications are portable from one trusted OS to another. So that's what I think is critical here for like long-term strategy. And then apart from that, we can start with like rusting the components as well. So first of all, I think we can start with the libraries which are provided by Opti, user space libraries. So these are not like Opti UT, that is the core library, but yeah, the other libraries which are being used by the trusted applications. And pseudo TAs can be a good starting point. It's like similar how we started with the Linux kernel. We started with the rusting the modules first, and then we move on to the core components. So yeah, similarly in the Opti side, we can have an API for the pseudo trusted applications to be written in Rust, and then move on to rusting the core components. Yeah, that's it mostly. If you have any questions at this point, yeah, let me know.
Thank you for your talk. In your Hello World trusted applicant, the TA example that you put up, there was an unsafe bracket around your params parsing. I'm guessing that has something to do with the internal things that it's doing to parse those parameters. Why does it need unsafe?
So actually, all those wrappers which we have on top of the C code, we are like that wrapper, that unsafe wrapper was like for parameters, to extract the parameters out of what is passed from the C code. So yeah, the bindings which we have on top of C library, that has to be unsafe over there. But yeah, as I said, right now we are piggy banking on top of the C library that is provided to us, but it should usually be we start with like the Rust library for Opti, but without a like portable APIs with the standardized API, it's difficult to do that. It's rather better whatever standardized API we have on the C side and rely on top of it. So yeah, the unsafe thing would be there, and we need to do that translation from C to Rust. So that would be there until we get rid of like the C library and write that in Rust overall. Yeah.
Thank you.
Anybody else? Okay. Thank you. Thank you for attending my talk.